Okay, hi, and welcome to Recitation 8. So once again, we are going with a recorded recitation because at the time of publication or during your normal recitation dates for this week, we were grading your exam. In fact, I'm recording this in between grading sessions. But yep, because of the exam and all that, we decided to cancel in-person recitation, but you'll be substituted with this. So yes, hopefully the exam went well. Hopefully your fall breaks were fantastic and well rested. And today we're going to be talking about independence, random variables, maybe a bit of graphs. I kind of forgot what the content is, but we'll get to it. The usual. Yeah, it is like 1 a.m., so bear with me. Let's get started. Okay, so first thing that we should talk about is independence, and we've kind of seen this a little bit in probability questions already, and maybe the word independent was just used all arbitrarily, and we never really associated a definition with it, so we're going to do that. By the way, there's a bright light from the projector in the same direction as the camera, so I might not make direct eye contact. Anyways, we say that two events, A and B, are independent if the probability of their intersection, A intersect B, equals the probability of A times the probability of B. This is a bidirectional statement. It's an if and only if, meaning if A and B are independent, then the equality holds. But also conversely, if we have this equality, then we can conclude that A and B are independent. It is incredibly important to be aware that this is the only definition of independence that we have. This is exactly what it means to be independent in the world of probability. The reason I harp on this fact is because sometimes we are tempted to substitute our own English definition for the word independent in probability questions, when in some cases, things that may seem independent from the English definition aren't mathematically independent. Therefore, we can only really call two things independent if they satisfy this equality. So I'm spending a lot of time on it, but independence shows up everywhere, and it's important to know that there is a distinction, subtle distinction between the mathematical and English definition, just a word of caution. It follows that two events, A and B, are independent if we have independent events and the probability of B is greater than 0, then the probability of A given B equals the probability of A. I'll show this on the board in just a moment, but if we think about this in words, and we will kind of use the English understanding of independence, so I am being somewhat hypocritical here, but it is for the sake of understanding. The probability of A given B, if these two are independent, then B shouldn't really influence the probability of A occurring, so it should just be probability of A. But we will show this mathematically to justify why it's true. And another point is, let's show it mathematically first and then come back. Okay, so this is the point that if A is independent, if A and B are independent, we can use this symbol here to denote independent. I didn't feel like writing it out. And the probability of B is greater than 0, then this equality will hold. And we can show this very simply by using our formula of conditional probability, where the probability of A given B is equal to the probability of their intersection divided by the probability of B. And now, using the fact that A and B are independent, which from our from the mathematical definition means that the probability of their intersection is equal to the product of their individual probabilities, we can do some sort of substitution. And here we see that the probabilities of B cancels. And this is just the probability of A. So that is the mathematical proof. Okay, back to the board. Okay, sorry if the video is kind of fuzzy. It's like kind of colorful or whatever on my preview, so hopefully that's not distracting. Anyways, we say that in a set of events, A1 through AN, are pairwise independent if for this, and let me just explain what this is. If for all ij in this range 1 to n, all pairs of values in this range 1 to n, the probability of the intersection of the events is equal to the product of the individual probabilities. So what this is saying is that from our set of events, if for all pairs of events, every two that I choose out, if they are, if this independence equality holds, we call the set of events pairwise independent. Yeah, and I guess conversely, if we're given this set of events and we're told that they're pairwise independent, then it's guaranteed that this equality will hold for every single pair. So the name pairwise sort of implies that we're looking at pairs of events. However, there's another vocabulary term which we'll turn to right now. So now we'll describe the word mutually independent, which again is used for a set of events. So mutual independence says, like, if we have a set of events and we're told that they're mutually independent, that means for every single subset of the values 1 through n, every single subset of events, we will have that the probability of their intersections equals the product of their individual probabilities. So it kind of looks similar to the definition of pairwise independence. The key note here is now we're taking any subset of these values, whereas pairwise independence was only 2 values from the set. One thing to note is that if we had this fact, that the probability of the intersection of all events, A1 through AN, equals the product of their individual probabilities, that does not guarantee that the events are mutually independent. It would have to be like every single subset has this, not just the one with all. Like, we're tempted to think, that's like the worst case or whatever, but no, it has to be for all subsets. So it is not a sufficient condition. And lastly, this is kind of the distinction between mutual and pairwise independence. Mutual independence implies pairwise independence, but the converse is not true. Meaning, if we have a set of mutually independent events, we also know they're pairwise independent. But if we have a set of pairwise independent, it is not necessarily guaranteed that they're mutually independent. And that's because in mutual independence, the pairwise case is already handled, right? The subsets of size 2, which is what pairwise independence accounts for, that's taken care of here, because we're considering every single subset. So yeah, that's the distinction there. Okay, now on to random variables. I realize I'm rambling a lot, but I just tend to do that. But I also like to give you a lot of information because I think small things might stick with certain people, and the more people that learn, the better. Random variables are going to appear a lot, basically from now till the end of our probability time here in CIS1600. Sorry, I'm so used to saying 160. But also well past into the world of probability. Like, it is used everywhere. So this is very important to learn. A random variable, in my opinion, is terribly named because, in my opinion, it is neither random nor variable. And I'll explain why in just a moment. Let's read the definition. A random variable x on our sample space omega is a function that assigns to each outcome in our outcome space a real number, which is x of omega. We haven't really studied what functions are, but the TLDR of what a function is like, you have some sort of input, you give it to the function, and it gives you something else out. Yes, this is important to note. A random variable, despite its name, is actually a function. So I don't think the word variable really makes sense, even though we usually use like x or whatever to denote it. It's a function. A random variable is a function. It's also not really random, because we're sort of like deliberately choosing what the random variable will be. Similar to how we define events for probability questions, we're going to end up doing the same thing for random variables. You'll see it when it comes to problems. So in that sense, I like to call them deliberate functions instead of random variables, but I'm the only one that does that, so yeah. Key thing, it's a function, and it's going to give us a real number output on each outcome. So when we're saying x equal to a, this is actually going to be the set of outcomes. So this is going to denote a set, and these are the outcomes for which the random variable takes on the value a. Meaning, if I go through every single outcome in my outcome space, and I apply the function x, a random variable, on that outcome, if that gives us the value a, then that will be a member of our set. And so to find the probability of, this thing happening, x taking on this value of a, we'll consider all outcomes such that the random variable takes on the value of a and add their probabilities. It's a bit abstract right now, but I think with a little bit of practice, it will make a little bit more sense. Yeah, cool, onwards. So more on random variables. There's a lot here, but I won't spend too much time on it since I've been rambling too much. If we sum over all values of x, over all real numbers, and take the probability that x equals x and sum all of those values, that will equal 1. because, x equals x, they're sets of outcomes, and they're going to partition our sample space omega. So what is key to take away from here is that, obviously this fact is important. But this fact about disjoint and partition is equally important. What that means is for every outcome in our outcome space, a correct definition of a random variable will have exactly one value, one real number corresponding to that outcome. So no matter what outcome I choose, the random variable must take on exactly one value on that outcome. That would be for a correctly defined random variable. Lastly, we have this notion of mutually independent for random variables. And it's again a similar thing where we take any subset of 1 through n and any values xi, so these are any real numbers. And if the probability of the intersection of these random variables taking on this real number is equal to the product of their probabilities, then again, mutually independent. This one is a little bit more complex, and admittedly it's really hard to explain it in words, so it's good practice to sort of write out this formula and just see what it actually means. Yes, I've been rambling far too long. Let's look into questions. Okay, so let's take a look at this first question. I highly, highly encourage you to have the PDF of the question available to you, because I simply just paraphrased it here, but I will explain the question. It's just, I only have so much room to work with. Okay, so we have these three buckets, A, B, and C. We are told that they're wooden, but I mean, they're labeled A, B, and C, so they're different. We also have n keys, where n is greater than or equal to 3. And we're basically throwing these keys into the buckets. We're told that the key throws are mutually independent. We are also told that each key is equally likely to fall into each bucket. And then some events are defined for us. A is the event that bucket A has at least one key. B is the event that bucket B has at least one key. C is the event that bucket C has at least one key. Part A is asking us to determine, are A and B independent? So we have just learned what independence is for events. So that's the first thing we should be thinking about. When asked to prove something, whether or not it's independent, you must do the mathematical equality and show that that holds. There is no sort of English argument you can make, because in math, you prove with math. Should put that on a t-shirt. Okay, so A and B are independent if we have A intersect B equals the probability of A times the probability of B. Remember, this is a bidirectional. If we have this, they're independent, and if they're independent, we have this. So we simply need to show that this equality holds. So yeah, we can choose which probabilities to compute. I'm going to start on the right-hand side. So the probability of A is equal to the probability that A has at least one key in it. I think this is a little bit difficult because we have so many keys. There's n keys. They could be falling into many different buckets. It's kind of hard to keep track of all of them at once. So what we could do is just narrow down our search more. Let's define events for each key. You know, if the first key falls into bucket A, maybe that can be its a certain event. If the second key falls into bucket A, that can be its own event. So even before I calculate this, let AI be the event. That key I falls in bucket A. So now we can write A in terms of these smaller events, right? We need at least one key to fall into bucket A. So we just need at least one of these events to happen. So this is going to be equal to the probability that A1 happens, or union, the probability that A2 happens. And if we just take the union of all of these, we can argue that they are equivalent. And I mean, it's a little bit confusing. The union of events, it just sort of doesn't sound right, but I will argue to you that it is correct. First of all, we should have defined a sample space and all of that, but that would take a little bit too much time and it's not particularly needed. But remember that events are sets of outcomes. They are a subset of the outcome space. So we are taking the union of these subsets and we're claiming that the union of sets is equal to this set right here. So the union is the correct operator to be using on events. And then further argument can be made as to why this is true, but I tried doing that best as I could. Okay, but now you're probably like, Ishaan, how am I supposed to find the probability of that? That's like utterly hideous. And maybe you're starting to think of PIE, but my goodness, that would make things even worse. So that's the thing. We just need one key to fall into bucket A, and the rest could do whatever they want. But it's hard to keep track of which key that is and when it falls in and blah, blah, blah. If we start to think in the opposite direction, like, what if we count complementarily and consider when nothing falls into bucket A? That might be a little bit easier to compute. So let's actually do that. If we start to think complementarily, the complement of this, well, to have an equality, we would do 1 minus the probability of this complement. We can now actually apply De Morgan's law on this to say that this is the probability of A1 complement intersect A2 complement intersect AN complement. So this is just by De Morgan's law. I would cite it, but I don't have much room. This is a lot more helpful to work with. We're dealing with intersections, which should start to think about independence. And we're also given that the key throws are mutually independent, which would indicate that we can use this notion of independence and decompose this into the product of the individual probabilities by our definition of mutually independent. So this, I'm going to use this big pi notation, which is akin to the sigma notation for sum, except now we're taking a product. Okay, so now we're just dealing with a single probability to calculate, and ideally this is the same for all values of I. But in words, this is the probability that the ith key does not fall in bucket A, right? We're taking the complement, it does not fall in bucket A. So it must fall in bucket B or bucket C. Something about disjointness you can argue there, but since each thing is equally likely to fall in each of these buckets, there's a 1/3 chance it falls into A, there's a 1/3 chance it falls into B, there's a 1/3 chance it falls into C. So the probability it does not fall into A is going to be 2/3. And indeed, that probability is the same regardless of which key we're looking at, right? Because the key throws are, sort of mutually independent, but also equally likely for each key. So we're just taking the product of this n times. We'll rewrite this as 1 minus 2/3 to the n. So that's our probability of A. What is the probability of B? Well, that's going to be the probability that B has at least one key. But if we were to compute that, we would do the exact same thing. We would let BI be the event that key I falls in bucket B, and then we would do probability of B equals a union, and every single computation would be the same. So this is going to also be the probability of B. That should sort of make sense, right? Because each key is equally likely to fall in each bucket, nothing different about the buckets. So the probability that, one bucket has at least one key shouldn't be any different from another bucket having at least one key. So this is going to be the probability of A and the probability of B. Now we just have to compute this last guy. Okay, so all we have left to show is the probability of A intersect B. We have to compute that, and then once we have that, we'll take the product, see if they're equal, and be happy and move on with life. So okay, how are we going to compute this? It's incredibly tempting to just be like, okay, I'll find the probability of A and multiply it with the probability of B to get this. But that's what we're trying to prove, so we can't just multiply the probabilities. Instead, we have to be in the set mindset. Set mindset. We have to think, what is A intersect B? What outcomes are in that set? And then, find the probability the traditional way. So this is going to be the set of outcomes of key placements such that A has at least one key and B has at least one key. So it could be like 1, 1, n minus 2. It could be like 17, 3, and then like the rest of them, it could be 1, n minus 2, 1, 1, n minus 1, 0, just like a ton of different possibilities. So a natural thought would be, okay, it's a lot of possibilities. What if we think complementarily, right? So what if we write this as 1 minus the probability of the complement of this, which after using De Morgan's laws, we can rewrite as the probability of A complement union B complement, and then find that probability. Okay, well, what does that mean? The probability that A does not have at least one key, meaning A is empty, or B is empty, right? So we could have 0, n, 0, 0, n over 2, n over 2, like 17, 0, the rest of them, or 0, 0, n. Still, there's a lot of cases. And sure, we can count it individually, like where A is empty and then the rest of the keys go in these two, and then consider the cases where B is empty and the rest go into those two. But then we have to be careful of overcounting, of when both of these are empty, and like subtract that out. Wait a second. Subtract that out because of overcounting. Doesn't that sort of sound like PIE? What if we were to do PIE on that? Let's write out what PIE tells us. The traditional PIE equation is given as follows. And so yeah, I could take that, put it in here, get the probability of A complement plus B complement minus, the complement of their the intersection of their complements. And sure. But it's always good to pause and make sure, like, am I going down the best path possible? And the reason I pause is I see probability of A intersect B right here, but that's what we were trying to solve for originally. So what if I just ignore this complementary stuff and just start with this PIE equation and solve for probability of A intersect B? So in fact, if we move that to this side and move this over to that side, we can rewrite the PIE equation to be this. And in fact, we can just ignore this altogether. Maybe this is a better path. And I will argue to you that it is a better path, because probability of A and probability of B, we've already got. So we just have this guy to compute. So let me make some space. Okay, so we have this, we just have to calculate that. So I'm just going to draw a line to delineate between the two, and we'll just stick with probability of A union B. Again, what does this mean? The probability that A has at least one key, or B has at least one key. And you're like, Ishaan, what are you saying? This has a ton of events in it too. You didn't make my life any easier. And yeah, like that's kind of my job, to make your life difficult. But let's take a moment to pause. Sure, it's a lot of different cases. And it was the same before with A intersect B. All that's really happened is now we're looking at a union instead of a intersection. The last time we had a union was when we were calculating the probability of A. We did the probability of A1 union A2 union blah blah blah. And we did that complementarily, negated it, did some sort of product, and called it a day. So we might be tempted to do the same thing. This is the 1 minus the probability of the complement. And again, we will use De Morgan's law. And this is what we had before, an intersection with stuff, and then we used the fact that they were mutually independent. And now we're in business, right? Because we can easily calculate the complement of A and B. No. Wrong. If you made this mistake, I do not blame you. I made this mistake. It was cut out of the video. I spent 5 minutes sitting on this desk at 1:30 a.m. figuring out why in the world this is wrong. It is very, very important in probability. I've been stressing this a lot throughout this example. Tell yourself in words what you are doing. I have numerously said like what A union B is in words, what A intersect B is in words. But here, I just jumped like this because I said, oh, yep, they were independent from before. No. Pull up the PDF right now because I erased it. The question tells us the key tosses are independent, which is why we were able to use mutual independence from before, the A1 intersect A2 intersect whatever, because we defined these in such a way to be based off of a single key toss. So these were mutually independent. These are completely different events. They're all of the key tosses looking at once. And in fact, it shouldn't make sense we can make this simplification because we're trying to prove it for without the complements. How can we just say that this holds if we haven't even shown it for this? This simplification you cannot make because the assumptions of the question do not tell us we can do this. It's super, super important to be careful with what you're doing. So, how do we proceed? I will say it again. What is this in words? What does it mean semantically? The probability that A does not have at least one key, meaning A is empty, intersected with the situations where B does not have at least one key, where B is empty. This is the probability that both A and B are empty, which means, what does that mean? That means everything must be in C. If A and B are empty, everything must have fell into C. So we can write this out like the probability that all in C. Now we just have to compute that probability. I don't feel like writing it all out because, dude, it's so late and I'm tired. Let me explain to you why. The probability that all are in C is equal to the probability that the first key toss goes in C. Intersected probabilities are like, you can take the intersection of all of these events, that the second event is like key 2 goes in C. Now we're looking at the key tosses. Those are mutually independent. So we take the product of all of them. The probability that a key falls in C is 1/3. So the probability all of them fall in C is 1/3 to the power of n. With this, we now have the probability of A intersect B. So I'm just going to erase this and say that this probability is equal to probability of A from before is this plus the probability of B minus this probability we just found. And to answer the question, are they equal to each other? Because that would tell us if they're independent. The answer is no. You can try setting them equal to each other and see if they actually are, but I will just tell you that they're not, and I just don't have the will to do algebra right now. But that's not the point of this class right now, doing the algebra. The point is just figuring out what independence means. Very long question, very tricky question, very important question. Hopefully that makes sense. There's still a part B. Okay, so part B is asking us to compute the probability that after all keys are thrown, each of the 3 buckets has at least one key in it. I realized C was never really defined in the question. I sort of just threw it in, but there you go, we need it. So really, B is asking us to compute the probability of A intersect B intersect C. All 3 buckets have at least one key in it. Hopefully that's not going off of the screen. It barely is, but who cares? Okay. Well, how can we compute this probability? It's easy. Right? We just multiply these probabilities. No, we don't. We don't. We don't multiply the probabilities because that would only be allowed if they were mutually independent. We don't know that, right? Part A showed us that A and B are not independent, which tells us that they're not mutually independent. That doesn't necessarily mean that this equality will not hold. Like, it could still hold. But since we don't know about mutual independence, since we disproved it in part A, like the result in A tells us they're not mutually independent, then we can't do this decomposition because we don't know this for certain. So what do we do? Same thing as before. When we saw an intersection and we couldn't decompose it by taking the products, we used PIE. So now we have a 3-set PIE, so let's write it out. So normally on the left-hand side, it's A union B union C, which you can write out and then move the terms around. I'm going to try to do it all at once, so hopefully this is correct. So that's our PIE equation. And already we're sort of in business. Probability of A and B we've already computed from before, and probability of C is going to be the same thing. And we can start to argue that, we'll come back to that in a moment. Probability of A union B union C. What is that? Again, before you start doing any sort of math, talk to yourself in words. What does this represent? The probability that A has at least one key, or B has at least one key, or C has at least one key. Well, that always happens, right? The keys go into the buckets, right? I have more than 3 keys. You know, one of the buckets must have at least one key. So no matter what, this will always happen. So this probability is 1. So no math needed, just able to figure that out with words. These 3 already computed. These 3, again, what are they in words? A intersect B is the probability that A has at least one key intersected with B has at least one key. So both of them have at least one key. And you should be able to argue that all of these 3 probabilities are going to be the same. And in fact, this value we computed in the previous part, but I have erased it, so shame on me. But you can rewind it and check it out. Now it's just a matter of substitution. 1 minus, these 3 are all the same, so I'm going to do 3 times the actual value. And then plus 3 times whatever this probability was from before. I don't think this is exactly what I wrote, but I'm sure it simplifies. If it doesn't, then I'll probably catch it during editing, but whatever. And now it's just math, which I'll just give you the answer. There you go. It was a long and tough probability question. I will definitely admit that. And I made a lot of mistakes. I will be completely honest with you. I'm terrible at probability. And a lot of stuff is just edited out because I made too many mistakes. The key thing I want you to take away from this is describe stuff in words to yourself. Do not always just jump into the math, because the math will take you down long, arduous paths which may not be fun. If you talk to yourself in words of what these things actually mean, it's going to make your life a lot easier. Be careful of when you're using independence based off of what things were assumed for. That's the end of that spiel, because I've been talking for too long. We do unfortunately have one more question, so let's take a look. Okay, so this is question 2. If you have not watched last week's recitation, I highly encourage you to watch it. Those of you who did watch it will notice that this question is eerily similar to a question we solved last week. In fact, it's identical. And I promised you last week that we would revisit this question, and I will make the same note that I mentioned there. When we publish solutions for this question, read them. We have published solutions by every single proof style you could possibly imagine. Everything works, so it's a really good study tool because you can try different types of methods. Last week we did contrapositive. This week, I think we'll do induction just to see what that's like. So yeah. Okay, so we're going to do induction. In fact, you can prove this by induction on vertices and induction on edges. I will choose to do induction on vertices. It is not always the case that in doing induction on both, or like vertices versus edges, will be will both work. One may be a lot easier than the other, but regardless, we're going to do it on vertices. There are small parts of this proof that will kind of seem confusing at first, and I will try my best to explain it as we go along. Just bear with me, and hopefully things will make sense. So let's define this P of n, where this will be that a tree with n vertices and max degree delta has at least delta leaves, just to make life a little bit easier. So we'll do induction. Base case, remember vertices are a non-empty set by definition of a graph, so we do have to test n equals 1. In this case, the only such graph we can look at is an isolated node. This has max degree equal to 0, which is delta. And indeed, we do have greater than or equal to 0 leaves. And now we would typically move on to the induction hypothesis, but I'm actually going to add a couple more base cases here. It's going to seem blasphemous at first, and yeah, it is, but it will help us out in the induction step. I could go through the explanation and then come back to why, the thought process of why we would need these extra base cases. I just do not want this video to be too long. So if you have such a question, come to concept office hours and we're happy to help there. But yeah, in this case, n equals 2. We're looking at a tree, so it must be connected. The only such graph is like that. We have delta equal to 1. We have 2 leaves, so we do have at least 1 leaf. So that base case also works. And then we'll test n equals to 3. We have 3 vertices. This is the only type of tree that it could be. It could also be like this or something, but it's, this 2 edges connected in such a fashion. Regardless, no matter what it is, delta equals 2, and we do have at least 2 leaves. So base cases check out. Induction hypothesis will be as per normal. We'll assume for n equal to k, change variables, bound by base case, that P of k holds. When you're writing your proofs, you should be a bit more, correct with your induction hypothesis. I'm just kind of scraping through it since it's been a long day. So now in the induction hypothesis, in the induction step, we're going to consider a tree T with k plus 1 vertices. Right, because we're inducting on vertices. It's very important in graphs that you start with the k plus 1, reduce it to the k case, and then reintroduce whatever vertex or edge that you're working with. In normal induction, mathematical induction, you could sometimes get away with starting from the k case and then growing up to the k plus 1 case. There are certain reasons why it's unadvisable to do so in graph theory, mainly because in mathematical induction, the mathematics we perform are bidirectional, which ends up making the thing work. With graph theory, it is not so much the case. Pretty poor explanation, a correct explanation, but that's my advice. Please take it. So we're starting with k plus 1 vertices. And remember, this is some sort of arbitrary tree. We want to reduce it to k vertices. What do we do? Well, obviously we remove a vertex, but we can kind of be careful with the vertex that we choose. We can choose a vertex that always appears in such a graph, right? If that vertex always appears, then we're chilling in the induction step. Since we're dealing with trees, trees always have leaves, so maybe we'll choose to remove a leaf. And the reason why we might choose to do this is because leaves don't really do much for the tree, right? When we're just removing a tree or a leaf, we just get rid of that. It's not connected to anything else except for one neighbor. If we were to remove some sort of internal vertex, it could disconnect a lot of other things, very annoying to work with. So leaf is just, it's off to the side, it's, enjoying its life, and it's not super damaging to our structure. So we'll let L in T be an arbitrary leaf. And let's let A be the neighbor of T, of L. Gosh, I should not be doing this at this time. Okay, we'll probably analyze this in a bit. So now let's get rid of L. Reduce it to a K vertex graph. So we'll define T prime, which is going to be the graph with vertex set V, which is from here, removing L, and then the edge set minus the edge L to A. Right, we're removing the vertex, but we also have to remove the edge associated with it, because edges, by definition, connect two vertices. So T prime is a tree of K vertices. So now we'll apply the induction hypothesis that T prime has max degree, we'll just say delta, and thus at least delta leaves. So sort of visually what we're doing here is we have this sort of tree. I chose some sort of leaf to remove, this one, so we got rid of it. This is T prime, which has, K vertices. We're doing the induction hypothesis. Now we want to reintroduce L and its edge and make a conclusion. Remember, we want to show that T has at least, we'll call it delta T leaves, where delta T is the maximum degree of T. So let's continue this proof. We want to reintroduce L and its edge, and this is only going to affect this vertex A, which we define to be its neighbor. Let's consider two cases. A being the vertex with this degree delta T, it could be that, or it might not be. So let's consider case one, that A is the only vertex of degree delta T. Well, okay, in this case, when we removed L, we had T prime. So in T prime, A has degree delta T minus 1. Right? Because we removed 1 degree from it. And so the max degree of T prime is delta T minus 1. And this is because A is the only vertex of degree delta T. If there was some other vertex of degree delta T, we'll handle that next, then this wouldn't be true. But since this is the only one, the resulting tree is at most this, because everything else originally was that or less. So therefore, T prime had at least delta T minus 1 leaves. But now we consider what happens when we reintroduce L. L is connected to A, and we know L is going to be a leaf in T, right? We know that L is a leaf in T. But did reintroducing L affect any of the leaves in T prime? No. The only thing it would affect is its neighbor, which is A, but we know A is not a leaf because it has this degree delta T minus 1. So when we reintroduce L, we're just adding 1 to the overall count of the leaves. So in T, there are delta T minus 1. This is from, whoa, that's on the curly brace, from T prime plus 1. And this is L, right? All of the leaves from T prime are going to remain leaves in T because nothing's being touched by them. The only thing that's being touched is A, which we know is not a leaf, but we add one total leaf. So therefore, in T, there should be a bound. There are at least delta T leaves. And so this case is handled. We're good. Okay, so now we'll consider the other case where, A is not the only vertex of degree delta T, but we know some other vertex has to have this degree delta T. We're defining that to be the maximum degree of the graph, so, something must have it. And we'll do the same thing. We had our graph that I conveniently erased, right? We called this L. This was A or something, and that's T prime. So upon removing L, the graph T prime, which is everything else, has maximum degree delta T. And this is because, like I mentioned before, when we remove L, the only thing it affects is A. But since A is not the only thing of degree delta T, some other vertex will still have degree delta T. So therefore, the maximum degree is going to be delta T. By IH, T prime has at least that many leaves. And again, we want to do this thing of reintroducing L and seeing how our count of leaves changes. So in this earlier case, we were just like, okay, well, A is not a leaf. When I reintroduce L, it's not touching any of the leaves. We know A is not a leaf for this reason. Therefore, we just add 1. In this case, we don't know anything about the degree of A. It could have been a leaf in T prime. It could not have been. So we have to account for both cases. So we'll call this case 2A. Well, if A is a leaf in T prime, when we reintroduce L to look at T, we are adding 1 to the degree of A, which means A is no longer a leaf, but L becomes a leaf. So in a sense, L is replacing A in the status of leafness, right? So in this case, the amount of leaves is still going to be at least delta T, because A is no longer a leaf, but L is now a leaf. So we minus 1 plus 1. Regardless, we've still proven what we aim to show. Lastly, we must consider the case where A is not a leaf in T prime. In this case, when we reintroduce L, it's not touching any of the other leaves, so all of the leaves from T prime will still remain leaves in T. So we are just adding 1 to the count of leaves. So and once again, this is greater than or equal to delta T. Therefore, our entire proof is over. This was complex. I will not, understate it. There's a lot to it, which is why I think this problem is so important. Do look through the solutions. Just make sure that this makes sense. It's good practice to try all of the solutions on your own. I'm gonna stop rambling because I know you're tired of me speaking. It's also 2 a.m. so I have to sleep and grade your exams tomorrow. So got a fun night ahead of me. Thank you for watching. Take care. Best wishes as you continue studying. Hopefully this was helpful to you. And just take care. Take care.